Hello, welcome to my channel. This is Obro, and we are meeting after long days. So today we are going to discuss a new topic, that is the gas power cycle. So gas power cycle, it is a thermodynamic cycle where the gas turbine and compressors are involved to generate power. So here we are going to start a good numerical on the gas turbine, as which is associated with the gas power cycle. So here the numerical is like this, that in an air standard Brighton cycle, the minimum and maximum temperature are 300 Kelvin, and one is the maximum is 1200 Kelvin respectively. The pressure ratio is that which maximizes the net work developed by the cycle per unit mass of the airflow. Calculate the compressor and turbine work each in kilojoule per kg air and thermal efficiency of the cycle. So here we have the data, that is the maximum temperature is 1200 Kelvin and minimum temperature is taken as 300 Kelvin. So now we have to first calculate. This is the cycle where we can see this is the path of the this temperature from 4 to 1, 1 to 2, 2 to 3, again 3 to 4. So this is entropy and this is the temperature. So now we will first calculate the optimum pressure ratio for the maximum work output. So the pressure ratio is given as Rp is equal to maximum temperature by minimum temperature divided by gamma divided by this is T max by T min, this to the power gamma divided by 2 into gamma minus 1. So gamma we will take as, this is the gamma we will take as 1.4. So gamma if we take as 1.4 over here, so we will put the value here, that is T3. T3 is nothing but 1200. So we will put here 1200, and this is T1 is 300. T1 is 300. So this is to the power 1.4 divided by the 2 into gamma minus 1 means 1.4 minus 1. So I hope you have understood. We have taken T3, that is 1200, and T1 is 300, and gamma is 1.4. This will take this value 1.4 divided by 2 into 1.4 minus 1. So if we calculate this, so this we will calculate, it will divided by 4, so it is 4, and so it will be 4 to the power 1.4 divided by 2 into 1.4 minus 1, that is 0.4 into 2, that is the 0.4 into 2, that is 0.8. So this is 0.8. So if we again divide this to the power value, that is 7 by 4. So it is 4 to the power 7 by 4. So if we calculate in scientific calculator, that 4 to the power 7 by 4, that will be 11.3. So we have to if we calculate 4 to the power 7.4, we'll get the value 11.3. So this is the optimum pressure ratio, that is the P2 by P1 we are taking as Rp, that is 11.3. We have calculated this value by putting these values here, we have got 11.3. So now in the process 1 to 2 process, this from 1 to 2, we will take that P2 by P1 is equal to P2 by P1 to the power gamma divided by gamma minus 1. So we will put our values over here, that is T2 is equal to, so T2 will be T2 is equal to T1 into P2 by P1 to the power gamma divided by gamma minus 1. So T2 is equal to T1 value we know 300 Kelvin, we'll put here 300. P2 by P1 is already we have calculated, that is Rp. Rp is nothing but P2 by P1, that is the optimum pressure ratio, that is 11.3 to the power 1.4 minus 1 divided by 1.4. So if we calculate this value in scientific calculator, that is 300 into 11.3 to the power, so 11.3 to the power, that is 0.4, 0.4 divided by 1.4, that is 11.3 to the power 0.4. divided by 1.4. So we have to calculate, this is scientific calculator, that we have to multiply with 300. So if we do using scientific calculator, we'll get the value 600.21 Kelvin. So we have got the value T2. We already have T1 and we have T3. Now T2 we have calculated. Now we will go for the process 3 to 4. So it is the process 3, from 3 to 4. It is T3 by T4 is equal to P3 by P4 to the power gamma minus 1 divided by gamma. So here we have taken that P2 is equal to P3, P1 is equal to P4. So we will put P2 in place of P3 and P1 in place of P4, and this to the power, this value will remain same, gamma minus 1 divided by gamma. So here we will do the same thing. We will put the same thing, that P2 by P1, that is the 11.3. So this is 11.3 to the power gamma minus 1. Gamma means 1.4 to minus 1 divided by 1.4, and that is equal to T3 by T4. T3 by T4. So if we calculate this, that is 11.3, that is 0.4 divided by 1.4, and we have one of the values, that is T3 we have. So T3 we have, that is 1200 divided by T4. So this we have to calculate using scientific calculator. So if we 0.4 means 2 by 7. So 2 by, we can divide numerator and denominator, 4 by 14. It will be 2 by 7. So just means T4 will be, so T4 value will be nothing but, we can move this 11.3 to the power 2 by 7 in the denominator, divided by 11.3 to the power 2 by 7. So if we calculate here 1200 divided by 11.3 to the power 2 by 7, we have to use the scientific calculator over here. So we will get the value 599.79 Kelvin, or we can make a 600 Kelvin if we round up the value. So here we have taken the heat supply, that is 2 3, that is 2 3 heat. Cp delta Cp is nothing but 1.005. So we'll put here 1.005, and T3 means T3 we have calculated over here. T3 we have 1200, that is 1200 minus T2. So T2 value we know 600.21. So 600.21. So if we multiply this 1.005 into the CP means the CP means 1.005. T3 is we have maximum temperature, that is 1200 minus T2. So T2 we have already calculated before. That is for the process 1 to 2, that is 600.21. So minus 600.21, if we calculate, we'll get us 602.79 kilojoule per kg. And now we will calculate the compressor work. Compressor work is denoted by WC, that is Cp into T2 minus T1. Cp is nothing but same 1.005. T2 we have T2, that is we have calculated 600.21, and T1 we already have in the data, that is the minimum temperature 300 Kelvin. So if we calculate this 1.005 into 600, so 0.21, it will be 1.005 into 300.21, we will get 301.71 kilojoule per kg. So now what is the turbine work? That is the gas turbine work. That is, gas turbine is working between T3 and T4 between this cycle. So Cp is same 1.005 into T3 minus T4. T3 is the maximum temperature we have got in the data, that is 1200 minus T4. T4 we have already calculated for the process 3 to 4. So here we will get, we already have 599.79. So we are calculating 1.005 into 1200 minus 599.79. If we calculate, we will get 603.21 kilojoule per kg. Now the final we have to find out, that is the thermal efficiency, that is the net work done divided by the heat supplied. So this is the formula. Net work done means WT, means what is the work done by the turbine, and other is the compressor work done by the compressor divided by heat supplied in 2 3. There are 2 3 process. So we have already calculated. So 603.21 minus 301.71 divided by this is Q23, that is 602.79. So if we multiply, we'll get 0.5002. So we have to bring in percentage in efficiency of percentage. So we will get 50.02%. So ultimately, we are getting the thermal efficiency for this entire system, that is 50.02%. So I hope you have understood how this full numerical has been calculated, where the work done by the gas turbine and the compressor in this gas power cycle. So I hope it was very easy to understand how the numerical has been calculated, and how what the formula we should use. Generally, for the heat supplied, we should use mcp into del T, and for the compressor work, we will take as cp into del T, and that also work done by the turbine, that is also cp into del T. So one is the cycle between T1 and T2, and other between T3 and T4, or vice versa. Here we have taken T1 and T2, compressor work has been done, and turbine work is between T3 and T4. So we have calculated the entire thermal efficiency of the system, that is 50.02 percentage. So I will end my video over here, and we'll continue with the next topic with the more exciting topics in my next video. Thank you very much.